In this lesson, I'll show you two examples on how to predict molecular geometries. Question 1 reads, find the geometry and bond angles of PCl₃. The chemical that we have here is phosphorus trichloride. The first step to doing this is to actually draw the Lewis structure. And in our case, P will represent the central atom. So we have P bonded to 3 chlorine atoms. So far we've used up 6 electrons. Each line represents 2 electrons. Keep that in mind. In addition, the valence electrons for chlorines are 7, and we have 3 of them. So 7 times 3 plus the valence electrons for phosphorus equals 5. So adding 21 plus 5, we have 26, and we've already used up 6. That means we have 20 more to work with. And these electrons will be distributed among the peripheral atoms. So starting with the chlorines, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 8 more, 13, 14, 15, 16, 17, 18, and the other 2 can be placed on the phosphorus atom. This has a complete octet, that has a complete octet, so do these 2 atoms. So we've drawn the Lewis structure. The next thing that I want to do is count the amount of bonding groups. A bonding group constitutes a single bond, a double bond, a triple bond, or even a single electron. So focusing in on our central atom phosphorus, we have 1, 2, 3 bonding groups. I want to count now the amount of lone pairs around the central atom, and we have 1 lone pair. Adding these numbers up, we end up with the total electron groups, which is equal to 4. So that represents the total electron groups. The last step is to take a look at this chart to determine the molecular geometry. So if you look closely, we'll focus in on these 3 rows. We have 3 bonding groups and 1 lone pair. And that gives us the molecular geometry of a trigonal pyramidal. And if you're curious, an electron geometry of a tetrahedral. One more thing to be mindful of is that if no lone pairs were present around the central atom, the bond angles will be that of an ideal geometry. If lone pairs are present, the bond angles may be smaller than the ideal geometry presented in this table. So because of the presence of the lone pair, the bond angles are a little less than 109.5 degrees. Let's move on to question 2. We're being asked the same question, except we have a new chemical, and that's ClNO. This chemical is referred to as nitrosyl chloride. We're going to follow the same steps as before. We'll start by creating the Lewis structure. So I'll write down Cl, nitrogen, and oxygen, like that. Chlorine, there's only 1 atom here. It has 7 valence electrons. Nitrogen has 5, and oxygen has 6. 7 plus 5 is 12, plus 6 is equal to 18. So far, we've already used up 4 electrons. That means we have 14 more to work with. I'll place those 14 electrons around the peripheral atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'll place the other 2 on the nitrogen. This has a complete octet. Nitrogen does not. We have 1, 2, 3, 4, 5, 6, but oxygen does. What we can do in this situation is take these 2 electrons, place them here. And so what we have is Cl having its 8 electrons, and with its lone pair, a double bond oxygen. The reason why the electrons were stripped away from the oxygen is because chlorine is more electronegative than oxygen. So the likelihood of oxygen losing its electrons is higher than that of chlorine. So this works best. We have our Lewis structure. Now we have to count the amount of bonding electrons. And for that, we will count 1, 2. So there's 1 single bond and 1 double bond. That accounts for 2 bonding groups. It has 1 lone pair. This tallies up to 3 electron groups. Let's use the chart. Focusing in on these 3, we have 3, 2, and 1. That gives us a molecular geometry that is bent, and this is what it looks like. The approximate bond angles for this type of molecular geometry is less than 120 degrees. And there you have it. 2 examples on how to predict molecular geometries.